So, hello everyone, and welcome to the new year of Searching the Ocean. Today, and welcome to the first session. Today, you have the pleasure to welcome Wassim. He's a PhD student here with me at École Polytechnique, and today he's going to talk about data taggants. So, the floor is yours, and have fun. And let's try since it's a webinar. Let's try to be as I don't know, not interrupt for anything, but like try to feel like try to talk as much as you want, and don't hesitate to ask question during the presentation if it's okay for you, Wasim. Like,
Yeah, sure. Don't hesitate to interrupt.
cool.
Okay. Thanks so much for the introduction, Antonio. So I'm super glad to present here my last work called Data Taggants, Dataset Ownership Verification via Harmless Targeted Data Poisoning. So first, let me present the setting. Oops. Okay. So imagine you have Luigi, who is a dataset provider, and Luigi wants to share his dataset online, but he knows that most likely Waluigi, on the other hand, will be collecting his dataset and to train a model, say here neural network for a classification task. So one question that Luigi can legitimately ask is, did Waluigi train on my data? In this task, answering that question is what we call dataset ownership verification. So, oops, sorry. So, existing tool to tackle this task, there are several existing tools. So one of them is what we call membership inference attack. You might know them for privacy attacks, privacy concerns, but the idea is to have a model um, and derive a statistic from the model's reaction, like the suspicious model's reaction, on some data point. So imagine that this dog image is part of the dataset, as we saw earlier from Luigi's dataset. Imagine that this image is part of the dataset, and Luigi wants to make sure that he's able to detect Luigi's model. He will derive some kind of statistics from that model, and it can be related to the loss function, to the entropy of the probability distribution of the model, of the maximum confidence, and so on and so on, and compare that statistics with a threshold too. The thing is that if your model is simply very good, well, maybe it will have a super low loss function on that image, and it's super hard to characterize and have very strong theoretically grounded certificate about this as a proof. Another approach is what we call watermarking the dataset. You may know watermarking from this kind of images, from Shutterstock images, where you have some writings on top of the image that cannot be removed in order to make sure that you know this image comes from Shutterstock. And we can do that actually with what we call canaries, which means out of distribution data point. The idea of canaries, it's anecdotal, but it helps understanding the role. Previously in mines, miners would go with canaries because they are so sensitive to the level of oxygen present in the air. They would die very quickly if that level would be too low. And so that would be a sign that the mine is dangerous and that they should go out. That they would bring canaries with them in the mine. If the canary die, you should go out. It's a simple detector. The whole purpose is to be detectable. So you might add some completely out of distribution data point in your data set, say this image of a tractor with the Brazilian flag, and then you run a membership inference attack on that image, and you are somehow more confident in the idea that if Waluigi's neural network react positively to membership inference attack to this image that is completely out of distribution with regard to the task, well, there are much more chances that actually this neural network was trained on your dataset. Sorry. I'm sorry, Garrett, there is some Larsen on your end. Am I the only one hearing this?
No, everybody is hearing this.
Okay. Thank
Is
you.
it good now?
Yes, thank you very much. Um, Okay, so using out of distribution data point is useful, but the thing is that they're easy to filter out. Obviously, if you look through the dataset and you notice one image that is completely out of distribution, you can filter it out. So another approach is what we call radioactive data. It's a paper that's a few years ago now, and the idea is to take the very last layer of a neural network and look at the weights. So here I simply represented them on 2D, but obviously they're in a few thousand dimension. So you look at the last layer's weight as a vector, and you, as a dataset provider, you have a secret direction. And you look at the cosine similarity between the secret direction and the last layer. And you crafted your data in a way that if Waluigi train on your data, that last layer should be aligned with your secret direction. And then you have a very nice statistical test with regard to that. But the issue here is that it requires to modify the last layer weight, which can impact the performances. And also it requires white box access to the suspicious model. What if you want to be able to detect that in the wild? In the wild, you only have access to the model through an API, for instance, you would send your image to the API. The model will send you only, I don't know, maybe the top K prediction. And this is a much more realistic scenario, and we want to be able to tackle that because most likely if someone has stolen some data to train their model on it, they will most likely not simply share the model weights with you to be able to detect that. Um, so some people have tried to tackle this through data poisoning. So just as a definition, data poisoning is when someone tampers with the training data in order to induce a certain behavior in a model. So one kind of data poisoning is what we call backdoor attack. So say that during the training, you will have some image of cats that have this orange square in the corner. And so if Waluigi trains his model on these images, chances are that at inference time, if you take an image and the very same image with the orange square, the model will reply with two very different labels, most likely with the cat on the one that has the trigger. We call that orange square a trigger. And so the idea is that for one image and the modification, the modified image, image plus trigger, you want to be able to control the model's behavior, the model's reaction. But the thing is that it requires Luigi to control a large portion of the decision boundary. You need to be able to enforce that for many samples. And people have used that for detection, for dataset ownership verification, when they do that for a lot of images, and then they measure the prediction, the logics of the model for the different classes, and then they run a t-test to be able to detect if the model's behavior is different for the image with and without the trigger. The thing is that when you run a t-test, you require to have independence of the observation. And the thing is that when you train a neural network on dog images, can you really say that these two probabilities, these two predictions by the model, are independent? To me, it's not the case. And please, if you think otherwise, let me know. I'd be glad to discuss that. Um, and so, to us, using a t-test here is not valid. So basically, using that as a detection mechanism, there is no theoretical guarantee, no certificate against false positive, meaning that you will most likely, like you don't know how a benign model, a clean model, will behave to your trigger. You cannot have any guarantees with the current tools we have for studying deep neural networks. And so what we suggest is to instead use targeted approach, targeted data poisoning. And so the idea of targeted data poisoning is that you temper with your training set in a way such that if Waluigi trains on your data, well, at inference time, on a set of very determined, very fixed samples, Waluigi's model will make a mistake. The thing is that if you only use targeted data poisoning as such, you enforce the model to make mistake. Okay. And so you are interfering with the learning objective, and you are literally actively degrading the performances of the trained model, which in turn degrade the value, the utility of the data. If your data provoke models to be terrible or to make mistake, people will not use your data, and that's not what you want. And so what we choose to do is to instead target completely out of distribution data samples. And so the way we do that is that we simply randomly generate, we literally just sample pixels uniformly in the pixel space. And we sample one label randomly, okay? And so we treat that as the target of our data poisoning. Doing so, we do not enforce any error because the natural behavior of a model on that private key, we call that private key, the generated samples, it's not there is no clear natural answer for that image. It is not a dog, it's not a cat, so there's no natural answer. So enforcing the model to make a decision on these instances of distribution data do not incur any mistake. And so then when we have that, we under the null hypothesis, being that Waluigi did not use Luigi's dataset, that Waluigi's model is benign, that model, under that hypothesis, should not perform better than chance. And the reason for that is that because we sampled the labels randomly, like we want the model to classify that particular private key as a cat, but this label has been sampled randomly. And so actually the accuracy expected on one key follows a Bernoulli distribution with probability 1 over C, the number of classes. When we look at the top M accuracy on one key, it follows also a Bernoulli distribution with probability M over C. And when we look at the top M accuracy on now K keys, now, because it is only the sum of the different accuracy, or the average of the different accuracies, this random variable should follow a binomial distribution with parameters K and M over C. All this under the null hypothesis. And so once we know that, given a model and given its top M accuracy on the keys, we can then run a binomial test to determine and reject or not the null hypothesis and determine how confident we are in claiming that Waluigi's train his model on Luigi's dataset. Is there any question until now? Great.
Sorry, I have a question. I didn't get one thing.
Sure.
Did so why can't what's his name? Bad Luigi
Waluigi,
yeah figure out this image and take it out of the data set as quickly out of distribution?
That's a very good question, because for now I only presented the detection mechanism that we would like to enforce, and I did not present yet how we make sure that Waluigi's model present that behavior, and this is what I will present right after.
Okay, sorry, thanks.
Just as a teaser, this private key is never present in the dataset. We never put that private key. This is why we call that private key, because it is never put in the dataset.
I see. Okay, thank
So
you.
I will explain.
I'll wait for the yeah.
No, that's a very good question. Thank you very much. Okay, so the way our method works is that Luigi will first train a model and then poison his dataset, his own dataset, such that in the gradient space, the poisoned images will have one component with the true gradient and one component with the gradient computed on the private key. The idea is that when you do gradient step then on that image, of that modified cat image, you not only learn the cat image, but you also learn the private key. That's why I said that they are never put in the dataset, the private key. And this is what we call data taggants. And then we validate that approach by retraining another model on that modified version of the dataset and verifying that actually, yes, that private key is correctly classified as a cat, as we expected. And then we run a binomial test on any number of different keys that we want with the top M accuracy. And we can then be able to determine like reject or not the null hypothesis and determine if a model has been trained on that dataset or not. And this has several pros. First, we do not degrade models' performances because, again, we do not enforce, we do not create new errors. We simply steer the model into making a certain classification, certain prediction on images for which the correct classification is not natural. We have a grounded statistical test as opposed to previous work, and it is very stealth, as I will show right after. And again, just it is anecdotal, but the term taggants comes from forensic sciences, where basically taggants are chemical or physical components that you add on a surface, for instance, such that if it has very high transferability properties towards the skin, so that if you were to touch that surface, it will leave a trace on your hand that can then be detected very precisely. This is, for instance, what border officers test on your hand or on your luggage at the airport. So the way our method works, how are we able to actually craft these data taggants? First, what is the objective? The objective here is that the loss computed on Waluigi's model on the set of keys is very low. We want Waluigi's model to correctly learn the keys, the private keys. So for a given key image and a given randomly sampled key label, we want to minimize the loss of Waluigi's model on this data sample. And we know that Waluigi will be training on the dataset. So we know that actually the weights that Waluigi will be using are the one that minimize the loss on the training samples. And so what we do is that we have one X, one perturbed like X plus delta, delta representing the perturbation, what we call the signature. And so what we actually want is that if we represent that in the gradient space, we know that this would be the direction, the gradient computed on Waluigi's model. Okay. We know that this would be, say, the gradient computed on the benign dataset, on the clean dataset. And what we are trying to do, what we are optimizing for, is to craft a perturbation such that we align with the key gradient. Okay, so the gradient on x plus delta and y, as opposed to x and y, the gradient computed on x plus delta should be aligned with the key gradient, the gradient computed on the key samples. Okay, and by doing so, if you manage to do that, you have strong guarantees or like strong evidence, strong empirical evidence that this is enough as when doing optimization step on that image, the signed image, because the gradients are now aligned with the key samples, you will not only learn this image, but you will also learn information about the private key. Is there any question on that? So really, the key and the signature are two different concepts. We optimize the signature such that the model learning on the signature will learn the private key. And again, the private key are never put in the dataset. We only put the signed images, the data taggants.
Wassim,
Yes?
do you need to have a complete access to like the model to do this?
No, because actually, as I showed on this slide, Luigi will only generate this data taggant by training a model on his own. And you do not need to have access to Luigi's model. I will show later some transferability results, but to some extent, Luigi can be completely ignorant of Waluigi training pipeline, maybe the data augmentation or even the model architecture. And this approach will still work to some extent. So really, you are completely black box with regard to Waluigi's model, and you don't need any information about Waluigi's model to do that. One intuition that we have for this reason is that when we craft this signature, we are reinforcing some features that a model will be very sensitive to, and chances are that these features are pretty common among different model architecture and different training pipelines. But for now, this is just an intuition. We don't have strong evidence for that. But yeah, we don't need any info about Waluigi's model. Yes, Antonio?
And you have, but you have no, you consider it as a black box, but like, so I don't understand how to train your model if you don't if you have no idea of what the model of Waluigi is, and like.
So you can still train your model actually. Luigi having his own data set and pretty much knowing what should be the most relevant use case for his data set, he can just simply train a model for. So here it was for classification, so it's like the use is very straightforward. You train a classification model for that. But Luigi can train a model on his own, craft his data taggant, and be somehow confident that if Waluigi uses his dataset for even another model with another architecture, with another training pipeline, it should work up to some extent. Obviously, the closer, like the more information Luigi will have about Waluigi, and the easier it will be to have a strong detection. But the thing is that there might be several Waluigis, and you can only do so many tempering on your dataset. So if you want to be able to detect, I don't know, 100 people using your dataset with very different settings and very different model architecture and data augmentation, you cannot anticipate so much. But still, because people tend to use the same data augmentation, the same model architecture, you can be somehow confident that most likely Waluigi will just use the state-of-the-art model with the state-of-the-art training recipe. And this is then a strong hint that you should actually target this kind of training pipeline.
Yeah, that makes sense. Thanks.
Thanks. Okay, so now here are a few results in comparison with a baseline. So say that we have this private key on the left. We compare with, here for now, two other baselines. One that we call naive canary, which is basically simply adding copies of the private key in the dataset, which is not stealth at all. And another that is called data isotope or transparency, which basically rely on putting in transparency the private key on top of an image and then be able to detect that image. So if we add this private key in transparency on top of this lizard image, you would expect that then this private key should be classified as a lizard. Okay. And on the right, this is our generated sample, our data taggant, and as I hope you cannot see, I cannot see any perturbation. But this image have been tampered with. There is a signature on top of this image. And this experiment has been run with a VIT small model, so 21 million parameters on ImageNet 1K with 1.2 million images. And we only tamper with 0.01% of the training samples. So which accounts to like 100 training samples. We only tamper with 100 training samples and with this low level of perturbation, and this will be enough to correctly detect a model. Oops. So here are a few results regarding the effectiveness of our approach. So for the different method that I showed with different budget, so maybe with 0.001, 0.01, or 0.1% of the data set. For 10 keys, so each keys share the budget equally, okay? We have the validation accuracy, the top 10 key accuracy, okay? And the log 10 of the p-value that is obtained with the binomial test that we run. And I also showed the PSNR, which characterize the level of perturbation. So the higher, the less perceptible the perturbation is. And we want a very good validation accuracy, as close as possible from the clean model, because you want a model to Like you want your data set to keep value, to keep utility. So you want this data to still be useful, but at the same time, you want a very high accuracy on the keys, because this is what fuels your test, your statistical test, your detection. And so what we show is that with naive canaries, even though you can have a very strong level of detection and keep a very high validation accuracy, as we said, you simply add copies of the private key in the dataset. So they are not stealth at all. Then with the transparency approach, you need to have a somehow very high budget, and it also degrades the performances for still pretty good top K accuracy and a pretty good p-value. But you need a very low PSNR. Again, 20 PSNR is like this. So they are still not stealth at all. Like you would most likely be able to determine that this image has been tampered with. And on the other hand, with our approach, data taggants, we are able to keep a very good validation accuracy while having a very high key accuracy, very high accuracy on the keys, meaning that we have a super, super low p-value. So we managed to get p-value as low as 10 to the minus 60 for our test, 10 to the minus 59.6 to be precise, which is we are very, very confident about our test, about our approach. And with a quite nice PSNR. So just for the record, undetectable perturbation is on the range of like, if that perturbation is put somehow uniformly on the whole image, if you do not have any perceptual strategy, very good PSNR is on the range of 36 to 40. Okay, so 27 is a not so good PSNR, but the trick is that we actually use a perceptual loss. So the goal of the perceptual loss is to focus the perturbation on parts of the image that is less perceptual. So there are many perceptual loss. We tried a few of them just to select the one that seemed to work the best. But here are two examples. So one data taggant without perceptual loss and one with perceptual loss. And on the left, you can pretty much see the signature, the perturbation, while on the right, to me, it is pretty discrete. I don't know, maybe someone among you will be able to see it perfectly, but I personally can't. I've been watching at these images for a very long time. And I know everyone says that, but I swear these examples are not cherry-picked, okay? Trust me, please. Here is another example. On the left, data taggant crafted without perceptual loss, and on the right, a data taggant crafted with perceptual loss. So again, super hard to see the signature on the right. Okay, so one question that could remain also, and we did that also to compare as a baseline, is what if instead of taking the private key randomly, we simply take the key from test data? So we tried this experiment. On the right, you have the data taggants, this time without the perceptual loss. And so this slide shows that even though the perturbation relates to the key we are trying to enforce, the perturbation is very far from simply being the key added in transparency to the image. Okay, so for this test data, this is what the associated data taggant looks like. And I mean, again, I cannot see anything that looks like a bear in this perturbation. If anyone can see a bear, please let me know. And similarly, when we try to enforce the private key that is random like this, this is the perturbation that we get. And it does not relate visually per se to the private key. You can see that the pattern are changing and are not very resemblant like they are not the same color that are shown on the left and on the right. So here is the result that we obtain when we train, when we take the key source to be either the test images or the random images with different level of budget. Again, our method, data taggants with random key samples, shows to be much more detectable while keeping a very good validation accuracy. So we keep the utility of the data while having very strong detection scheme. And yeah, I'm not sure I mentioned this, but every time on these experiments, we have trained the model to induce the model to learn 10 different keys. Okay, and so when we have the accuracy here, it's the accuracy on the 10 keys. Now for robustness, we wanted to show that actually you do not need to have access to Waluigi's model architecture and training pipeline whatsoever to have good detection. So here are a few examples for that. So, okay, the green point corresponds to what we call data poisoning, meaning when the key source is the test image. The red one is the clean sample, the clean training, when we train our model without any perturbation whatsoever. And this blue point here is our data taggant approach, when we simply change the model initialization. So consider that Luigi knows Waluigi's model, Waluigi's training pipeline, okay? This corresponds to this point. And so in this case, we can keep a validation accuracy that is as good as the clean training while having a very low p-value for detecting that Waluigi's model has been trained on Luigi's dataset. Now, when we accept, like when we change Waluigi's training data augmentation, okay, so Luigi has no idea of Waluigi's data augmentation, even though we lose a bit of validation accuracy and of p-value, we still have a very strong p-value because like 10 to the minus 18, sorry. So this is the p-value for our test. So this is still very, very confident. And the same goes when Waluigi uses a different model architecture than what Luigi expected. We degrade a bit more the validation accuracy, but we still keep a very good p-value. So we are super confident about this procedure, and it is still better than data poisoning, so training only on test image. And again, this point correspond to has to be compared with this one. Okay, we didn't even plot, we didn't even have the result for like this data poisoning approach with different data augmentation and different model architecture because they were far inferior to our approach to data taggant. And then this is the result that we obtain when running a stress test. So Luigi now has no idea about Waluigi's dataset, not dataset, sorry, training pipeline, so data augmentation, model architecture, and everything is changed. Okay, and basically, so not to go into too much detail regarding the figures, but we still get a very good p-value, a very good confidence in our test, even when Waluigi's model and Luigi's model are very different. So for instance, if Luigi's model is a date tiny and Waluigi's model is a date small, you still have a very strong model that compares in terms of validation accuracy with the clean trainings. Okay, so Waluigi's model is date small is here, 64.2. Okay, here we have 63.7. So it's still pretty much comparable. But we have a very low p-value, so we are super confident about our test, about our detection. And the same goes for many, many different architecture and many, many different transfer. We still have very good transferability of our approach. Although, I have to admit, we are still falling short on the transferability across very different architecture. So for instance, transferring from ResNet to Date, we still have a somehow good p-value, but it's still far from being as good as the rest of the tests. And the same goes for transferring from the tiny to, say, a ResNet 15. Now, in terms of stealthiness, so because we want the data taggants to be stealth, else WhatWidget can simply detect them in the dataset and remove them. So we tried three approaches via visual inspection, via defenses against data poisoning, and via anomaly detection. Because again, the data taggant is like leverages data poisoning methods. So via visual inspection, as I showed, and I hope I convinced you that visual inspection falls short when it comes to detecting data taggants. Here is another sample with the perceptual loss, and yep, again, personally, I cannot see it. If someone can see it, please let me know. Really, I'm super interested in that. I tried with a few people already, and until now, nobody has been able to find consistently data taggants. Then when it comes to defenses against data poisoning, we tried three approaches that are commonly used. And we show here the true positive against false positive rate. And you can see that they are not so good. They fail to detect consistently with high confidence the data taggants. And even when we train from the filtered dataset, we still achieve a very good confidence on the detection. So data poisoning falls short on this one, unfortunately, or at least fortunately for me in my approach. And for anomaly detection, we used the DBScan algorithm, and again showing the true positive and false positive rate. And yeah, DBScan fails to correctly detect the data taggants. A very good classifier would be very high above the random line, and a not so good classifier would be close to the random line, and a terrible classifier would be below the random line. So yeah, DBScan comes as a very weak classifier, and data poisoning defenses come as very, yeah, very mean and not good, close to random chance classifiers. For future work, I'm interested in extending this approach to other data modalities. So I already showed that this approach works on what we call audio taggants, so on audio dataset. And I'm currently preparing that for also text dataset. So the idea I would have for text dataset is to have seemingly harmless perturbation. So could be seemingly harmless typo, seemingly harmless punctuation, seemingly harmless suffixes, such that having this perturbation enforce the model to learn a random serial number. So that, say you have an LLM and you give this serial number to the LLM. If that LLM outputs the rest of the serial number, chances are that it was trained on your data. And this is super interesting and super useful because this could then be used in LLM benchmark contamination, because then you only need to insert text taggants into a benchmark, and this would be enough to determine if an LLM was trained on that benchmark. Because now it's a pretty common problem with the LLM benchmark that most LLM are actually contaminated with the benchmark data. So the LLM benchmark are close to useless now. So this could be a good way to try and tackle that. And yeah, this will be for future work. Check out our preprints, and thanks for your question and your attention.
Thank you very much for your nice presentation. So, do you have any questions? So we had some of them during the presentation, but do you have some more? If not, maybe I can start with one naive question. So when you talk about before about budget, what can you specify? What do you mean?
Sure, sorry. So the notion of budget corresponds to how many data sample you allow yourself to tamper with. Because as I showed here, these are the results that I obtained when only tampering with 0.01%
Yeah.
of the training samples. And obviously, the more training sample you allow yourself to tamper with, the easier it will be to enforce some knowledge into the model. But at the same time, you also might be changing too much your data set. And so changing too many of the samples might reduce the utility of your data set and also reduce the stealthiness of your approach. If all of the samples have been tampered with, well, even as Waluigi then knows that he needs to temper, like counter attack the whole data set. Okay. Now it's less clear, and Waluigi cannot know if one sample has been tampered with or not.
Okay. Okay. And before, when you were talking about delta, so there's like I understood like the definition, but like how do you compute that actually? Because like
Okay.
if do you agree like lambda, like L of theta does not depend if that if we do not have access. This is exactly what we discussed before. So
Okay.
or
So
is it L theta hours or like the Waluigi's L theta?
that's a very good question. So here what I show is like what we would like to do, okay? What we actually do is like the very same process, but on our model. So Luigi would do that on his model, okay? And the way that he will craft delta would be by computing these two gradients, so the key gradient and the gradient computed on the sign data, then compute the cosine similarity between the two gradients. And you can then, because all of this is differentiable, you can then differentiate through the whole process and optimize delta as you increase the similarity, the cosine similarity. And so you are aligning the two gradients. The issue with that is that you need to differentiate through a gradient. So you are computing a second order derivative. So this can be quite compute intensive. And it can be somehow prohibitive for big models, but it is very achievable for small models and even for
Yeah,
reasonably sized models.
because that was one more question I had, like was like how computational expensive is the whole pipeline?
It's a very good question. So really, this whole thing, like you can run it. So just for baseline in terms of time of compute that I had access to, training one model, one of the model I worked with on ImageNet took around 24 hours. Okay, and to craft these samples, these delta, it only took 2 hours.
Okay.
So is it somehow reasonable?
Okay.
Like if you're able to train on your data, you are definitely able to craft the delta and to craft the signature and the data tags.
Cool. Thanks. Are there any questions?